Hello everyone, thanks for being here. My name is Aman Sheikh, I'm from AT&T Labs, and today I'll be talking about peering Dragnet and so how do you go about identifying violations that your peers might be doing and what you can do about it. And so this is a joint presentation with a bunch of folks, Tom Scholl, Nathan Patrick and Richard Steenbergen. So this is just a little artwork from Tom actually. In case you don't know what Dragnet is about, this gives you some context. And so if you have more questions, I'll refer you to Tom. So what is this all about? As you all know, peering is all about two networks or two service provider networks coming together, agreeing to some rules and so that they can exchange traffic, each other's customers' traffic between them. And so some of these rules are just to sort of bring you up to speed is, first of all, consistent announcement across all locations, only sending traffic to routes that you announce to your peer, only announcing internal or customer routes, and whatever else the two parties may agree to. And so basically peering is an act of trust, but at the same time you want to make sure that your peer is not violating any of these rules. And that's what this presentation is all about. It's about trust, but you want to go ahead and verify that your peer is agreeing to the rules. So we have a tool that looked at peering announcements that we are receiving in SBCIS 7132. So most of the examples in this presentation have been caught in real life. Of course, we have changed the names to protect the guilty. So how can a peer actually violate the rules? How can he pull a jack move on you? Before I say that, let me just hash what we really mean by peer violating the rules. It can happen either because peer wants to steal service from you or resources from you, or it can happen unintentionally due to some configuration mistake, for example. And so on this slide, I have a few instances of how a peer goes about violating the peering rules. For example, one of the sort of most widely known or obvious way of doing it is sending you inconsistent announcements so that you would send your traffic to specific locations and you would carry peers traffic on your network. That's kind of well known. People are kind of aware of it, but then there are these other violations that might happen which are not so well known, sort of quite obscure. For example, peer might send traffic to unadvertised routes, the routes that you may never have advertised, and to obtain free outbound transit. Or peer might send you more specific routes. This is something where your peer and your customer might get together and send you more specific routes so that your customer gets free inbound transit. Another subtle way of violating rules is where a peer sets up tunnel between peering endpoints and uses you as a free backbone transport. And I'm going to mostly focus on number one, which is about sending inconsistent BGP announcements to force you into cold potato routing. And then later on, I'll give you some insight into the last three ways of violating peering rules. So let me move on to inconsistent BGP announcements. Before I say that, let me say that the consistent announcements basically ensure hot potato routing. And so when you have a traffic that you want to dump onto your peer, you send it to your peer's network as soon as possible through the closest exit. And this is sort of best common practice because it's, at least conventionally, it's supposed to be good for traffic and routing quality, and you basically use less resources on your network and send the traffic off to peer's network as soon as you can. Unfortunately, there are a number of ways in which your peer can actually send you inconsistent announcements. For example, he can send you a different or more specific route at certain locations and less specific routes on other locations. What that's going to do is that it's going to force traffic through the peering locations that your peer wants you to use, and which can basically force you into cold potato routing. Or he can prepend advertise AS paths with peers ASN, or he can play with AS path length, for example, to make some routes look better at certain peering locations and worse in some other peering locations. Or he can play with origin code, use IGP in some cases and incomplete in some other cases, for instance, to again force you into cold potato routing. And these are some of the things that we check actually. Now, most networks would only make some cursory attempts to verify. For example, look at MAD values or look at total number of prefixes that peer might be sending at different locations and see if there is any discrepancy there. We go beyond that, look at a lot of different things in the route announcement that we receive from the peers. So even if you want to go ahead and detect these inconsistent announcements, they are not always very easy to detect. And one of the reasons is that BGP only installs and propagates the best route. So if you are using a centralized BGP monitor or a centralized route server, all you are going to get is the best routes from every peering location. So for example, if you have a peering location where you have a bunch of peers, you're probably going to see only one of those routes, not all the routes from all the peers. So you essentially don't get all the information. And so the only sure solution is to actually examine adjacent rib-in or the rib-in that exists on the peering router, or received routes in other ways, to say it differently. And there are a bunch of different ways in which you can do this. One is to sniff or tap at the peering circuit. Now this may or may not be feasible in production. It might be feasible on some locations, might not be feasible on some other locations, might not scale well. Another possible approach is to debug BGP updates that you might receive from the peering routers through a BGP monitor. This of course gets complicated because you have to do some inferencing. You have to look at the updates and try to figure out if your peer is violating the rules or not. And this is actually something that has been explored in the past. If you look at IMC 2004 paper by Nick Feimster called Border Guard, this paper exactly does this. It takes BGP update from a BGP monitor and then tries to infer if peer is violating some of the rules. But again, it gets complicated and might not even be feasible in some cases. The third approach, and this is the approach that we take, is to execute CLI or netconf commands on every peering router. And this is the approach that we take. And so I'm going to discuss this approach in more detail and the results that we obtain through this approach in next few slides. So next I'm going to describe you the exact approach we took. And the first task is getting the data. Second task is running some of the checking for inconsistencies essentially on the received data. And the third task is doing some long-term analysis. So let me start with how we go about getting the data. As I said, we basically get the data by running commands on the router CLI and collecting ribbon routes from the peering locations. Now, one way to do that is to use netconf, which is a recent standard effort to get to basically use XML transactions methods to get information out of the router. Now, there is also a working group in IETF for standardizing this effort. Now, one problem with this is that this may not actually be may not be completely standardized in the sense that some devices might support this and some of them might not. So this might not work with all the routers that you might have in your network. Also, some of the Perl XML parsers might consume a lot of RAM on your server. So the other approach which probably is guaranteed to work on almost all the routers out there is Telnet SSH. It's not as pretty, but like I said, it's probably going to work on almost all the routers that you might have. And so essentially you just run CLI commands to get the received routes, to view the received routes on the peering router and then redirect this output through TFTP for the processing. Of course, RSH works too, but it obviously has all the security problems with it. So we basically use Telnet SSH approach to get the data from peering routers. Once you get the data of the peering routers, once you get routes from all the peering routers, these are some of the checks that you can do for every peer that you might be peering with. For example, is peer sending same number of routes at all locations? This is probably one of the first high-level check that you might want to do on the tables you get from the routers. Or is your peer sending your RFC 1918 addresses? These are private IP address space and something that your peer should not be sending you. It's very conceivable that you might be using this address space to number your own infrastructure, in which case it's going to lead to all kinds of problems on your network. Or there might be other addresses that you might be using on your infrastructure. Might not be private address space, but you might be using public internet address space to number your infrastructure. So you might want to check for these addresses in the peer's announcements. Is your peer sending you /25 to /32 mask lengths in the prefixes? And sometimes you do permit this behavior, but usually the rule is that peer should send you these routes with no export mark on it, but some of them don't. So it's probably worthwhile to check for this. Going to some other checks, these are more specific checks. I mean, I'm going a little deeper here, where you're checking things on every peer, prefix pair. So first thing you want to check is the peer announcing a given prefix at all locations or not? Even if number of locations are, even if total number of routes at all locations are same, the prefixes might not be same. So even if you have a case where your peer is sending same number of routes at every location, you might still want to check if a given prefix is appearing at every location or not. Even if you have a route that's being announced at all peering locations, you might want to check if the route is same from BGP decision point of view. And here it's not just about looking at the best route that a router selects, but you want to actually simulate BGP decision process up to hot potato step. You don't want to go beyond hot potato step because that's going to depend on your IGP. But you basically want to look at things like MED, origin, AS paths, and so you want to see if your routes have consistent BGP origin, AS path, and MED. Inside AS path, you can look for things like loops. Now, when I say loop, you don't want to just look for AS numbers that repeat in the AS path, because with AS prepending, that's quite likely. What you really want to see is if there are ASs that might appear non-consecutively in your AS path. And that's what you want to look when you're looking for loops in AS paths. And we have some examples that will show you that this happens in real life quite often. Or is your peer sending you private ASNs in the AS path? Do you observe your own AS in the AS path? So these are some of the things you can check on every peer, prefix pair once you get the data. There are a few things you can do in terms of long-term analysis by looking at snapshot across time. I mean, one of the obvious things to do is to track inconsistencies over time. Is your peer playing tricks based on time of day, just to shift traffic around as load or demands change throughout the day? Or these are more one-time thing that the peer is doing just to sort of carry him over some of the problems he might be having in his network? There are a bunch of other different ways in you can use the data. For example, you can use this data to configure and sort of retune your max prefix counter and increase it over time by looking at the routing table size that your peer is sending you. Or you can, if you see fluctuations in this routing table size, you can probably use it for troubleshooting. Or a long-term increase in the table size, that's something you can use for capacity planning purposes. You can also probably look at customers behind your peers and see how the business relationships are evolving, which customers are moving across peers and things like that. So there are a bunch of other uses also of this data, not just peer auditing, so to speak. So these are some of the challenges that we faced when we collected the data from SBCIS. First of all, polling from routers takes significant amount of time, in the order of a few hours. Now, given that BGP updates occur so frequently, essentially in the time scale of seconds, this basically means that you might not have a consistent snapshot across all your routers. You might be in the middle of a BGP convergence process while you are collecting the snapshot. So sometimes you might catch some of these transient inconsistencies that might be happening during BGP convergence. Essentially, we need a better method to retrieve data from all routers in a more scalable, reliable, and efficient manner. That's something we plan to pursue. The other question is, how often should you poll? If you poll too frequently, you're going to impact the production routers. If you poll too infrequently, you're going to miss some of the fine time scale violations that peer might be doing. So it's kind of a trade-off, and right now we settle for once a day, although we probably will go for a few snapshots every day just to get day of time behavior in the future. So this is our solution in nutshell. We call it the peering Dragnet tool. There are two components, route retriever and route analyzer. Route retriever is the component that retrieves data from all the routers. So it has a script that logs into the routers and runs show IP BGP command to get all the received routes, puts this output in a file. Typically, we have one file for every peer, peering location pair. And once we have the data, we have another component called route analyzer, which actually analyzes these routes for some of the violations that I mentioned earlier. And it generates reports of all the inconsistencies and anomalies. So what data did we look at? We basically looked at routes received in SBCIS, AS7132. We looked at both inbound and outbound routes. In case of inbound routes, we looked at pre-policy and post-policies. That is, routes before the policy was applied and inbound routes after import policy was applied. Here we'll mostly be talking about post-policy inbound routes only. We also looked at outbound routes, like I said, but for obvious reasons, we won't be talking about that here. We are in the process of collecting data in the sense that we have started it in mid-August, and we are still collecting the data. Right now, we are collecting one snapshot every day. So, and so we have about total snapshots, and I'll be presenting results for August 9th through September 30th snapshots. So we have about 50 snapshots there. So here is a slide showing overall results, overall summary of what we found so far for the 50 snapshots that I told you about. What I'm going to do is, for different kind of violations, I'm showing you what's the normalized average, what percentage of time we found violations on an average for every snapshot, along with the standard deviation, just to give you some sense of the variability involved in the data. So the first aspect is, how often is peer cold potatoing 7132? And we found that when we look at total number of routes at different peering locations, about 64% of the peers had some discrepancy. So they were sending different number of routes at different locations. So there was which is quite high. I mean, we were surprised to see that. What this basically means is that 64% of the peers were doing something in terms of peers by not announcing at some locations or by announcing some more specific prefixes at some other locations to play some tricks. Now, when we sort of deep dive into individual prefixes or individual routes, we found that about 2.3% of the routes were missing at some locations. So they were visible at some locations, and then they won't be visible at some other locations. We also looked at attributes, and we found that few of them have different origins at different locations. Now, some of these percentages might look quite small, 2.3 or 0.003, but remember that we're talking about few hundreds of thousand routes that we might be receiving from peers. So when you convert them to absolute numbers, they are still going to be a reasonable number, which would kind of make it somewhat hard if you have to manually go after each of them. Going back to the results, again, different AS path lengths, we found that about 1.6% of the routes had different AS path length at different locations. Slightly changing the angles, how many routes were inconsistent? Well, we found that about 0.16% had /25 to /32 prefixes. We didn't find very many instances of RFC 1918 address space violations. There was only one snapshot, and there were few route leaks in that particular snapshot. 0.087% AS paths had loops in them. We didn't find any unallocated ASNs in AS paths, which came as a big surprise. We were expecting at least some violations, but fortunately we didn't find anything. We found about 0.005% cases where AS paths had private ASNs in them. So in next few slides, I'm going to talk about some of the interesting cases that we observed in the results. So let me start with BGP origin inconsistencies. And we found quite a few interesting cases in for this particular violation. For example, we found that some Asia-Pac peers were de-preferring some of the West Coast peering locations. And that's probably got to do with the limited capacity that they might have on their trans-Pacific peering links. For example, there was an Australian peer which was advertising one route at Palo Alto and Seattle, and he was clearly indicating us to prefer Palo Alto for inbound traffic into his network. Or there was another Asia-Pac peer which advertised a bunch of prefixes with different preferences at LA and Palo Alto. Looks like he was preferring Palo Alto for us to enter his network. Similarly, there was an Oceania peer doing something similar. Another Asia-Pac peer was doing something similar again. We found another case where it seemed like another Asia-Pac peer again, who seemed to be doing some load balancing. He had a bunch of prefixes. One set of prefixes he was preferring Palo Alto, and another set of prefixes he was preferring San Jose for us to enter his network. So this looks like some fancy load balancing going on here across trans-Pacific peering links. Moving on, there was a Canadian peer which advertised 1/23 and 1/16 at Chicago, New York, and Seattle. As you can see from the origin values, he clearly seemed to be preferring Seattle over New York and Chicago. Now, what's really interesting here is that the /16 seemed to be set of broadband users out of Ontario. And so the question is, why would he want us to go through Seattle in order to route to Ontario? Why would he want us all to go all the way to West Coast? Maybe due to some peering capacity issues in New York and Chicago. Interesting thing about /23 was when we ran some ping and traceroute probes, we found that the probes died right at the first hop. So it's not even clear whether there is any real host behind this prefix or not. Another domestic US peer which advertised a prefix at San Jose, Ashburn, and Atlanta. Now the customer was based in DC, and again he was preferring us to go via Atlanta instead of Ashburn. Not clear, maybe a misconfiguration or peering link issue. It's not clear. Again, another domestic US peer which had 2/24s which were being advertised in LA and Chicago. Now, again, the closest peering location was actually being depreffed in this case. Like LA was being depreffed for our wine customer, and Chicago was being depreffed for Chicago customer. So, fairly interesting, not clear what's going on. Capacity issues, misconfiguration, could be any one of them. This is something about RFC 1918 address space leak. Like I said, we didn't find very many leaks. There was only one snapshot which had a leak from a large cable MSO. And these are the set of prefixes that he leaked. And it covers a fairly wide range if you look at it. 8/5, 128/1, it's like almost half the address space. 10/8. This lasted only for a day, so probably a misconfiguration or something on the cable MSO's part. Some observations about ASN loops. What we observed was that AS paths, when they had loops, had this particular form. So you had basically the AS which was forming the loop, there was another AS in between. So you had something like BBB, then XXX, and then a few more occurrences of BBB. Now our conjecture here is that it's probably ASN BBB which is doing the prepend, so that they can essentially make sure that ASN XXS would drop the route. Again, this looks like some form of traffic engineering and load balancing, essentially to make sure that large network would send traffic on the inbound link that they prefer and not on the lower capacity link. So most of the times the XXX that we found were large networks. But then there were some cases where it looks like that these were just plain typos. I mean, 11139 and 1139 looks like an obvious typo there. We found quite a few cases actually. Maybe what we really need is a command where you can just say, prepend this AS 5 times, and not something like where you actually type those 5 ASNs to prevent these kind of typos. Continuing for AS paths, we found that these ASNs that were injected in the loops, injected in the paths, the XXX, they seem to be spread across the globe. So we had like 5 ASNs from Europe, 7 from North America, 3 from Asia Pac, 1 from Latin America. So you can see a wide geographic span as far as these ASNs are concerned. Now what's really interesting is that when we looked at the ASN that prepended the route, the BBB in previous slide, they followed roughly the same geographic distribution. So we had 6 from Europe, 7 from North America, 3 from Asia Pac, 1 from Latin America. So it looks like that ASNs, when they prepend something and when they put another AS in the path, it usually seems to come from the same geographical area. A few observations about unallocated/private ASNs. Like I said, we didn't find any unallocated ASNs in our analysis. We found a few cases of private ASNs. For example, we found about 20 unique peers advertising paths with private ASNs. And again, here we see a reasonably wide geographic span: 7 North American peers, 9 European peers, 4 Asia Pac peers. Found about 73 unique prefixes that were received across all these peers with private ASNs. Most of them belong to /19 through /24. There was one peer which had multiple private ASNs, 65001 and 65500. Quite interesting, though not sure what's going on here. So this is as far as results for BGP inconsistencies are concerned. Next, I'm going to talk about some of the more obscure ways of violating peering agreements. So let me move on to the second type of violation that I referred to earlier. This basically occurs when a peer sends you data traffic for which you never advertised a route. Now, the thing to keep in mind is that even if you didn't announce a route in BGP, there is nothing that says that the peer cannot actually send traffic to you for that particular route. This is more likely to happen at a public internet exchange, especially when you don't even have any relationship with them. Now, in theory, this is fairly easy to detect, because if you have traffic coming from peers that you don't peer with, that should be fairly easy to detect. But how do you go about stopping it? You don't have any relationship with the other guy, and so what are you going to do? You can't go and talk to them, or even if you go and talk to them, they might not listen or flatly deny that something like this is happening, or they might claim it's an accident. But if you actually have a peering relationship, then it gets even harder to detect, because you have to really distinguish between real and unauthorized traffic. So that makes it a little hard to essentially isolate the traffic that the peer should not be sending to you. Now, there are basically 2 ways to combat this forced traffic forwarding routing behavior. Either you do some accounting, which is basically detecting the bad traffic or unwanted traffic after the fact, or you do some filtering to prevent it from entering in your network in the very first place. I'm going to talk about both of them a little bit here. So how do you go about detecting it? Essentially, what you want to do is check for traffic that's coming on the wrong link, wrong peering link. So you can use NetFlow, for example. Essentially look at the source address in the data packet, whether it makes sense or not. So you look at source and destination and see if it really makes sense, whether you should be receiving packet with those source addresses. Now, the problem with NetFlow is that it doesn't tell you anything about the peer that sent you the inbound traffic. Thus, it might only be useful when you have a private peering, when you have a point-to-point link with your peer, and not a public internet exchange where you might be, where there might be a lot of service providers that are connected through a switch. Another alternative is to use MAC accounting, and here the idea is that when a traffic arrives on your peering link, you want to map the source address of that. You basically want to use source MAC address of the packet to determine what the remote router was, and then check if you have an eBGP session with this remote router. Now again, this may or may not be possible depending on your line cards and other factors. So you might end up using a combination of these techniques, net flow, MAC accounting. You might also want to use ECL counters for specific sort of filters and see if those counters are going too high to detect this unwanted traffic. Now that was about detection. How do you go about preventing it in the first place? Surely prevention is better than cure. Well, there are a few ways. What you essentially want is an NT default provisioning/configuration. And what I really mean by this is on your peering router, you don't want to have a default route. You only want to carry your customer or internal routes, no default route. Now, at least during .com era, one of the ways of doing was to just have a separate peering router, completely isolate it, only carry customer and internal routes, and carry no default. Of course, this doesn't quite work well now that we are sort of in .bomb era. But maybe with Dow hitting 12,000, it might again make sense. Anyway, even if you do that, it basically means extra cache. I guess the better solution is to actually do it virtually, essentially combine best of both worlds. So on your router, you can use routing instances or BGP policy accounting to prevent these kind of violations. Currently, Cisco can probably do this with QPPB in some platforms, and Juniper might also Juniper can also do it on some platforms. So essentially, you have your virtual fibs that you use for inbound traffic that carries no default and only customer and internal routes. Another possible approach is MAC filtering. It might not be as powerful, but it can probably prevent individuals that you don't peer with from sending traffic to you. Basically, you block traffic that comes from certain source MAC addresses, especially when some internet exchange providers provide you with accurate MAC address to IP address mapping. This probably makes quite a bit of sense. So next I'm going to talk about another way in which peer can violate the peering agreements. For example, and this basically happens when you have a customer and peer that collude against you. They get together and form a tag team and conspire against you essentially. It's a little bit more complicated and that's why it's kind of obscure and nobody usually checks for it. But here is how it happens. So I have the textual description here. On the next page I have a same thing as a figure. So don't worry if you don't get it through the text. The idea is that let's say you have a network A, which is a customer of network Z. B is another network which is a peer of C. Now let's say your customer A becomes transit customer of network B. And so A and B get together. What they do is that network A would announce more specific prefixes of its address space to network Z. And then network B, and then network B would go ahead and send it to the customer's actual provider network Z. Now network Z would only get less specific aggregates. So what it sends to the internet is this less specific aggregates for the customer. The net result is that when traffic comes from internet for network A, it hits network Z. Now network Z has the less specific aggregate as well as the more specific aggregate. And so what it's going to do is it's going to use the more specific aggregate during forwarding, send it to network B, and then the traffic comes through network B to customer A. Since the link between customer A and provider Z is not being used, customer A is essentially getting free internet connectivity without paying anything. So the bottom line is that it's the customer A and your peer B, which is essentially pulling the jack move on network Z. Now this is the same thing through the figure. If you look here, network A is the customer, Z is the provider, B is peer of Z. Let's say A's address block is 1/16, and that's what he sends to network Z. And that's the prefix that network Z announces to the internet to make this customer visible in the internet. Now what network B does is that it announces more specific /24, 100/24 and 1010/24 to network Z. So now when the traffic hits network Z, like I said earlier, it's actually going to get diverted to network B and then will flow to customer A instead of going over the provider customer link. So again, network A and B has formed the tag team to victimize network Z. It's quite subtle and interesting, but this is something you might want to check for. And why does this work? Even though most smart networks would use local preference for customer routes over peer routes. Now, the key thing is that the routes are different here. What customer is announcing is a /16 in the example. What peer was announcing /24. So the first check really doesn't apply here. And the way forwarding works is more specific prefix is what is preferred during forwarding over a less specific prefix. The way to prevent it is to actually check if you are receiving, for every customer block, are you receiving more specific routes from your peer? That's the thing that you want to check for in your BGP routing to prevent something like this. This is the final violation that a peer can do. The basic idea is that, especially now that tunneling is fairly widely used in the networks, this becomes a real possibility. Essentially, the idea is that if you have two peers, network A and Z, and if you have multiple peering locations with /30 assigned to those peering circuits, network A can essentially establish a tunnel through this peering link. And let me just show you the picture which will basically make it more clear. So here is your network Z and then network A, which essentially establishes a tunnel through the peering routers in San Jose and Ashburn. Now what happens when traffic hits San Jose on 1001/30 side, instead of going through the peer's backbone, it gets tunneled through your backbone. And so essentially your peer is getting free transport through your backbone. Now, why this might not be noticed is because /30 is something that you might have assigned, and so you might not really check for something like that. The way to protect against this is you basically want to look for unusual amount of traffic going to the /30 assigned to the peering link, or you might want to rate limit the traffic. So with that, let me just summarize what we had in this presentation. Peering Dragnet is all about detecting peers that might be violating one or more of the peering agreements. What we have right now mainly just looks at the control plane, BGP announcements, and whether those announcements are consistent or not. The results that we have so far based on AS7132 have demonstrated a variety of different ways in which peers might be violating some of the rules. This could be for traffic engineering or load balancing or some capacity issues, or it could be some misconfiguration and typos as well. One thing that I wanted to point out is that even after these violations are detected, we need to do some more careful analysis to kind of understand why this might be happening or what's really going on. And we probably would like to automate some of this as well. But apart from this sort of obvious and well-known ways in which peer might be violating rules, there are some sophisticated and subtle ways in which they can violate the rules as well. For example, they can do it in data plane by sending traffic to the routes that you may have never announced. Or it could be the case where your peer and your customer gets together to play a tag team on you and essentially steal free inbound traffic. Or with tunneling becoming mainstream, it could be through tunnels where a peer establishes a tunnel through you and gets a free backbone transit. The bottom line is that in all these cases, you want to pay very close attention to the control and data traffic that's coming into your networks from the peers. And with that, I'll be happy to take questions.
Yeah, Danny McPherson. I've got a couple of questions actually.
Okay.
Did you guys do any analysis of meds and peers using that for gaming? I saw that you listed it, but I didn't see that you actually listed any of the analysis of it.
So I think the answer is, and Tom, correct me if I'm wrong, we mostly looked at inbound routes after policy was applied. And in that case, were we setting meds to 0?
No, we were looking for the pre-policy, but we had the post-policy data as well. But
Yeah, okay.
No, I believe the dumps that we actually ran the studies on, it was on pre-policy before we applied any RFC 1918 filters and AS path filtering. So it was on pre-policy. But as for meds, since we were looking at pre-policy, we had the natural med values there.
Okay, so yeah, no, I noticed one of the slides said that all this was post-policy, and you
nah.
didn't give the pre-policy act.
Yeah, we didn't include the
It was a
results. But
mistake.
yeah.
And so no, it's all pre-policy. So we're seeing. The
Oh, it is
actual-
pre-policy. Okay, that changed. So that was one question. The other question I was going to ask actually is, or a recommendation is, there's some work in the IDR working group in the IETF that's about multipath advertisement, and there are a number of different mechanisms, either entire adjacent ribbons and the full contents of that, or also the best path from each BGP peer on a given BGP speaker, or there are also some other alternative mechanisms, and it makes detecting things like this much easier. Some people want to use it for like multipath and other things, but for route analysis and peer gaming and whatnot, it's really useful for that as well. So just recommendation that if you guys are interested, you have a look at that work. So thank you.
Okay, that's a good suggestion. Thank you. Yeah.
Philip Smith from Cisco. This looks very similar to work that was started about 18 months ago by Gaurav Upadhyay and Vijay Adhikari in Kathmandu. And they've presented similar type things at the APNIC meeting and SANOG. And they've been talking about publishing some of the path anomalies that they've been seeing. And I was just wondering if you were going to consider doing a similar thing, because I think it'd be quite useful, at least in our part of the community in South Asia and Southeast Asia. We thought this would actually be pretty useful to make people aware of weird things that were happening. And I think it would be a good service to the community to actually highlight some of these things.
So when you say publishing, sort of publishing on the web on an ongoing basis so that people can look at the reports, or you mean more like a research publication or a magazine publication?
No, I think on an ongoing basis, I would find that actually quite useful. I mean, certainly, their work was presented at SANOG in Karachi a couple of months back, and the feedback there was, wow, this is actually really interesting stuff, and maybe try and publicize this a little bit, just to make service providers aware. It might actually be an idea if you speak with Gaurav and Vijay as well. Maybe you can do something jointly to publicize it, because they've got different views of the world as well from what you have.
Okay, I mean, we would definitely be happy to talk to them and might consider doing something like that as well. We haven't thought about it, but I think that's definitely a possible venue for this work. Yeah.
Okay. I mean, just that you mentioned that you were protecting the innocent or the guilty or whichever, but I think maybe just mentioning some of the guilty people. I mean, I mentioned the guilty people in my routing report that I sent to the NANOG list, so I don't get too many brickbats for that, so I don't think you should fear too much about it either.
Well, yeah, that's fine. I mean, but I don't think you want the names here, right? Do you? I mean, I don't even remember some of those names top of my head, but yeah, if we actually put the reports, we won't be protecting the guilties for sure.
Okay, thanks.
Sure.
Ren Provo, AT&T Peering. Tom did bring some of the anomalies to my attention, and we did write to the peers. A couple of them corrected. A couple others mentioned that they had congestion in 1 or 2 points. We did not write to the peers that had the typos. Probably we should do that in the next round.
Sure. Thanks.
I mean, the typos, I mean, they're really not impacting anything, but I mean, it's one of those things that, at least if you're originating it, you probably should correct it, I would think.
Okay, any more questions?
That's it. Thank you.
Thank you.